Hello, welcome to this short presentation on piecewise-defined functions. These are functions in the same sense that you're already familiar with. They are relations where each input has exactly one output. If you were graphing them, they would pass the vertical line test. Or the VLT. Or you might have thought about a function machine, where you put something in, it spits something else back out, never spits out two things at once. And, all those definitions. So it's still that, but it's broken up into pieces so that it's defined differently on different parts of its domain. So you're going to see the function notation, like f of x, but now you're going to see more than one little equation. And then you're going to see off to the side, like, what's going on with the x's. So, like, the first part of the equation might be, is this part if negative 3 is less than equal to x less than 1? Or the second part if x equals 1. Or third part if x is greater than 1. That's just an example. The numbers aren't necessarily exactly like that, but it'll give you the equation, the little equation, and then it'll give you the domain over which that part is defined. All right, let's do an example. Okay, let's say we have f of x equals negative 2x plus 3 for x is less than 1, and then 3x minus 2 for x greater than or equal to 1. So those two pieces, you might recognize them when they stand alone as two linear functions. But we're going to put them together and have each piece only exist in certain parts of the domain. So once this is graphed in its entirety, it'll still pass the vertical line test. Nothing will overlap. Okay, so like negative 2x plus 3 by itself is a line. And it's for x less than 1. So I'm going to still plug in 1 because I need to know what that endpoint looks like. But that endpoint's going to be an open circle because of the less than and not less than equal to. Then I'll just think about, what's happening for other values less than 1. So if I plug in 1, I get 1. If I plug in 0, I get 3. If I plug in negative 1, I get 5. So let's see here. So 1, 1, nice little open, like an open circle. 0, 3. Definitely a closed circle. And then negative 1, 5. So when you connect the dots, it still keeps going up and to the left, but it stops here at this open circle. Then 3x minus 2, that starts at 1 and includes 1. So plug 1 into that, and we actually get 1 back. We won't always get the same point. Plug in a 2, you get 4. Plug in a 3, you get 7. I probably won't even go that far. So 2, 4, like that's going to actually fill in at 1, 1. Like earlier that was an open circle, but now it's going to be filled in because of this second piece. 2, 4, and like if you did 3, 7, So then that looks like that. So it almost looks like an absolute value graph, but it's not, because the two pieces of the V have different slopes. But there you go. So there's the entire function. Passes the vertical line test. And that particular function, the domain is all the x values. It's negative infinity to infinity. Because even though it has that V shape, at the point at x equals 1, it is defined there, thanks to that second piece. The range, well, the lowest and the y's it goes is 1. And then it shoots up to infinity. And then it is continuous. Like if you were to try to trace the graph with your pencil from left to right, you never actually have to pick up your pencil. You have the V shape, so your direction changes some. Like you go from decreasing to increasing on the function, but you don't actually have to pick up your pencil or anything. And then if you were wanting to talk about intercepts, no x-intercept because it doesn't actually cross the x-axis. But for y, it goes through the y-axis at 0, 3. Okay, so that's a little bit about that piecewise defined function. Let's look at a couple more examples. This next one to me is a little more interesting than that previous one. Of course, my definition of interesting is probably different from yours. The first piece, you can tell, is a linear function when it stands alone. But we're going to have this linear function so that it's not defined at x equals 0. So basically at 0, 0, it's a nice open circle. Okay, but otherwise it has a slope of 2, so you can go up 2 over 1, or you could go down 2 left 1, and it's this beautiful line. It's just this beautiful line has that open circle at the origin. Now at the origin, we're told that the function has the constant value 1. So at 0, x equals 0, we do that. So this is a discontinuous graph. At x equals 0. Because if you were tracing the graph, you'd have to actually pick up your pencil there and hop to that lone point, and then hop back down and then keep tracing. So that's the situation there. But the domain is still negative infinity to infinity, like the previous example. Because even though it's discontinuous at x equals 0, it still has x values defined there. The range, on the other hand, is a little different. The range goes from negative infinity to 0, union 0 to infinity. In other words, at x equals 0, or I mean at y equals 0, sorry, it doesn't have a value. It's not defined there. Now, when y is 1, you've got 2 values. That's okay. Like, remember, with domain and range, if there's repeated numbers, you don't have to address that or write them twice. We just have to address where things are missing, where these gaps are. So at y equals 0, it has a gap. So that's discontinuous, domain, range, and then intercepts. Again, no x, because like at the origin it's an open circle and it doesn't touch the x-axis otherwise. But y, it has that point at y equals 1. So 0, 1 is the y-intercept. All right, so if you thought that was interesting, hold on to your seats because we're about to get even more interesting. So this one, you see 3 parts. Two of the parts are linear. One of the parts is a constant. This is going to have some really fun stuff going on. Gosh, I'm sorry for not drawing this super straight. And hopefully I don't mess up trying to lay out mark my grid here. Find that if I go by 1 unit, it's too small. So I'm trying to go by 2 units to mark it out. But I'm also like, my vision's getting worse as I get older. So just pause for a second, double check, make sure I marked it okay. I think it's all right. Okay. So for x plus 3, I'm going to pay attention to what's happening at the endpoints at -2 and 1. But at -2, I'm allowed to have a nice closed dot right there, -2, 1. Excuse me. But at 1, 4, I'm going to have an open dot. Because look at the domain. It's -2 less than or equal to x. So at -2, it's included. But then it's x less than 1. So at 1, it's not included. Slope of 1. So it's this little piece here, like a half open line segment. Then at x equals 1, it's 5. So you have a nice closed dot there. And then for x greater than 1, it's -x plus 2. So once again, we'll go ahead and put in 1 just to see what that endpoint looks like. But it'll be an open circle. So at 1, 1, it's going to be an open circle. 2, 0, 3, -1. And that's linear, so it's just you can draw a nice smooth arrow going down to the right. All right, so what do we have as far as analyzing what's happening here? This one again is discontinuous, but this time at x equals, well, I guess again, a discontinuous at x equals 1. Because you definitely have to pick up your pencil when you get to x equals 1 and move around and like hop around. Hop around twice. Hop up, then hop back down. Then domain. Well, this graph has a solid dot at x equals -2, so domain actually starts at -2. But then as you trace to the right, at x equals 1, it has a y value. It's defined there. And then you can keep tracing to the right forever and ever. So domain goes -2 to infinity. With the range, it shoots down to -infinity. Coming up at y equals 1, it's defined, so we're good there. But at y equals 4, you have that open circle, and there's no defined point at y equals 4. And then there's a gap, and it hops up just to the value of 5. And then there's nothing else. So you have an interval from -infinity to 4 for those y values. Union, just that discrete value 5. So that's domain and range, the continuity. Oh, and then the intercepts. What do we want to know about those? It crosses the x-axis at 2, 0. It crosses the y-axis at 0, 3. And there you go. So that's another piecewise-defined function. It has the pieces, it's a function, passes the vertical line test, and it has different definitions across its domain. All right. Well, thank you for joining me on Piecewise-Defined Functions.